Welcome back, everybody. In this video, we're going to finish up section 4.4, which is on counting methods. We've done most of the work already. We just have a few loose ends to tie up. So I wanted to begin by recapping what we had gotten to last time, at least the highlights. So the main things we've gotten done were we talked about the fundamental counting principle, and then especially we had defined the factorial notation. Whereas you can see here, if we have n factorial, that is n times n minus 1 times n minus 2, and so on, all the way down to 3 times 2 times 1. And what this tells you is the number of ways of arranging n items. Okay, and that's basically a special case of the fundamental counting principle. That's ways of arranging all of a particular set of items. If you're making subsets of a given size, then it's going to be either permutations or combinations. If you have n total objects and you're going to select r of them, the number of ways of making that selection of r objects is either PNR or CNR, depending on whether the order the selections are in matters or not. In other words, it's permutations if the order the items are in matters, and combinations if the order they're in does not matter. And that was basically where we had left it. So here I wanted to start by doing another couple of examples just of making the calculations. So that's what we'll do right here. So the first thing to do is we want to find CN1. So then let me just repeat the formula here for you. CNR is going to be n factorial over n minus r factorial, In this particular example, our n is n still, but our r is 1. So here we will have n factorial. That'll be divided by n minus 1 factorial, and then 1 factorial. Okay, so then we can do a little bit of simplification. So going back to the definition, remember that n factorial is the same as n times n minus 1 factorial. So then when you divide by n minus 1 factorial, something nice happens. The 1 factorial is just a 1, so we can dispense with that. Here the two n minus 1 factorials cancel, and you're left basically with just n. And in hindsight, that should make sense. If you have n total objects and you need to choose one of them, how many ways are there for you to make that choice? It should be pretty clear that there's n ways for you to choose one item out of n of them. Okay, so let's try that again. We want CNN this time. So this will be n factorial over n minus n factorial. This time the r is the same as the n. So then we'll have n factorial again. Okay, and so now n factorial divided by n factorial is just going to be 1. And then n minus n is 0. So we'll have 0 factorial times 1. Remember that 0 factorial is not 0. It's actually equal to 1. So we'll just have 1 for this. And again, this should appeal to your intuition as well. If you have n total things and you're going to choose all of them and the order they're in doesn't matter, there should be only one way for that to happen. And so that should make sense. Okay, so let's try this next one next. This next one will take maybe a little bit more care. So, but we'll try. So we'll have n factorial, and we're trying to take n minus r objects. So that will be down below. We'll have n minus and then n minus r. This time instead of an r, in place of it, we have n minus r. And then we'll have n minus r factorial. Okay, so now this will take some simplification. So in the denominator, in the first set of parentheses, we're going to distribute that negative. So we'll have n minus n plus r factorial. And then down below, we'll have still n minus r factorial. All right, so now n minus n is 0. So we will just have n factorial. And then down below, we're going to have r factorial and n minus r factorial. Okay, and notice that this is the same as CNR. So this one is especially kind of interesting, I think, that CNR is the same as CNR N and minus R. Okay, and what that means, or an example that illustrates it, would be like this. Let's say that you have, just to keep it easy, let's say that you have to have, or you have 6 books, and you're going to pack 2 to take on a trip. And so the question might be, well, how many choices of 2 books are there? First of all, what makes this combinations is the fact that the order that you choose the books in doesn't make any difference. They're just going in your suitcase, okay? So the 2 books are either selected or not selected. The order that they're in doesn't matter, which is what makes it combinations, okay? So we're packing 2 books to take on a trip. So if you think about it, if you have 6 total books, and you're going to pick 2 to take on a trip, let's say this one and this one, then when you're making that choice of 2, you're actually also choosing the 4 that will not go on the trip, right? The N is 6, the R here is 2, and 6 minus 2 is 4. So when you're choosing the 2 out of the 6, you're also simultaneously choosing the 4 that are not going on the trip with you. And that is basically what this statement right here says. When you're choosing R items out of N, you're also simultaneously choosing the ones that are left over as well. All right, so what I wanted to show you next is something interesting called Pascal's Triangle. And what Pascal's Triangle is not like a geometric triangle. It's more like a triangular array of numbers. And as you'll see, it ends up having a nice application to the counting methods topics that we've been studying. So the plan basically is to talk about how Pascal's Triangle is constructed, and then how do you read it, and what does it have to do with this counting stuff that we've been working on. So the first thing to do is to just to see how Pascal's triangle is made. And so it's, like I said, a triangular array of numbers. The first row has just the number 1 in it, right? Starts off easy. And then the next row has 2 ones in it. Okay, and then the next row doesn't have 3 ones in it. It has 1, 2, and 1 in it. And then let me write out some more rows, and then we'll talk about the pattern that you can use to construct this triangle. So we have 1, 3, 3, 1, 1, 4, 6, 4, 1, and then we'll have 1, 5, 10, 10, 5, and 1. Okay, so here's the first couple of rows of Pascal's triangle. I wanted to point out how this triangle is constructed. First of all, it's, like I said, a triangular array of numbers, and the start and end of each row is a 1. So each row starts and ends with a 1. And then other than that, each entry in the triangle is the sum of the 2 kind of entries above it. So here, 1 plus 2 makes 3. 3 plus 3 makes 6. And then 4 plus 1 makes 5. 6 plus 4 makes 10, right? So to see how the next row then would be constructed, it would go like this. The first row, or the first entry in each row, is a 1. Then 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. Then 10 plus 5 is 15. 5 plus 1 is 6. And then the last row, or the last entry in each row, is a 1. The other thing that you'll notice is that there's some symmetry in the entries. This started 1, 6, 15, and then it ended 15, 6, 1, right, with 20 here in the center. So there's also some symmetry involved as well. So that is how the triangle is constructed. So I wanted to show you next, what does this have to do with what we've been working on? So let's do that. Okay, so to relate it to what we've been working on, we have to come to an agreement about how we're going to label things. Rows and columns are going to start with 0. So we'll say start counting rows and columns at 0. Okay, so here the first row is not going to be row 1. This will be row 0. Okay, similarly, the row right here with the 6 in it, that is row 0, 1, 2, 3, 4. That is row 4. It's physically the 5th row in the triangle, but we're going to number beginning with 0 so that we'll call that row 4. Similarly, columns will start with 0 also. So this is in column 2. Why? Because this one is in column 1, column 0. 6 is in column 1, and then the 15 will be in column 2. Okay, so each row and each column begins with a 0. So let's try this out. We're going to find the entry in, let's say, row 3, column 4. Okay, so let me try that. Row 3, column 4. So 0, 1, 2, 3. So this is row 3, column 0, 1, 2, 3. There is no column 4. So let me make that column 2. Sorry, that was kind of anticlimactic. So 0, 1, 2, 3, 0, 1, 2. So that is the row 3, column 2 entry. 0, 1, 2, 3, 0, 1, 2. So when you're counting down by rows and counting across by columns, you begin at 0 is the whole point. Okay, so finally, what does this tell you? What does this give you? The thing is that this tells you C32. In general, in Pascal's triangle, the row in column R entry is CNR. Okay, so if you need to figure out CNR, you don't have to necessarily use the formula for this, especially useful if you have several to figure out because you can write out the table. Of course, this is in a way limited usefulness. If I asked you to find out like C17.8, okay, you're not going to necessarily want to write out that many rows of this table. But if you want to go up to maybe 5 or 6 or something, then writing out this many rows of Pascal's triangle is not too bad. You just have to decide what the trade-off is. For something like C17.8, it's going to be faster for you to use the formula than to write out Pascal's triangle. If you have relatively small numbers, and especially if you had several of these to figure out, then it may be worthwhile to write out Pascal's triangle. I like to show Pascal's triangle in part just because it's, I think it has some intrinsic interest to it. The other thing that I wanted to mention off of Pascal's triangle before we go further is the symmetry, right, that we saw. Here, row 0, 1, 2, 3, 4, 5, column 2. This is C52. You'll notice that C53 is also 10, right? And that basically goes back to this fact that we just showed a couple of minutes ago about how if you're selecting R items, that's the same as saying the number of ways of selecting the other items, right? And so that's why you end up with this symmetry. CNR is the same as CN minus R, the rest of it. Okay, so that's enough basically about Pascal's triangle. The rest of the video here, we just kind of want to work through some additional examples of different counting type topics. Okay, so let's continue. So for this one, the story is you have 3 coins. We want to know how many ways there are for you to get it exactly 1 tail. So I've written out the sample space for you so that you can take a look. We want to know how many ways there are to get exactly 1 tail. So there are 1, 2, 3 ways of getting exactly 1 tail. So the answer to this question is 3. Okay, I wanted to bring this up because that's different from this question. What is the probability of getting exactly 1 tail? Well, here there are 8 possibilities. Our sample space has size 8. So there's a 3/8 chance. Okay, remember that all probabilities have to lie between 0 and 1. Okay, the count here, 3, is a number of ways that something can happen. The probability is just an expression of the chance or likelihood that that event happens. So make sure that you pay attention to the directions on the question. Are you asked for the number of ways something can occur, or are you being asked for the probability of something in particular occurring? Okay, all right, so then question going back to a deck of cards. So for this one, the story goes like this. 5 cards are drawn, and we want to know the probability of getting exactly 3 of a kind. So if you're still a little hazy on what a deck of cards looks like, you might want to pull up an image of that on your phone or your computer or something to look at, or get a deck of cards and take a look. We want to know the probability of getting exactly 3 of a kind. And I did want to mention also that for the scope of this question, the other 2 cards are going to be considered different from either of the first 3 cards, or any of the first 3 cards, and also different from each other. That is, when we're getting exactly 3 of a kind here, we're not going to count 4 of a kind, which would have been possible. And we also don't want to count situations like where you might get 3 jacks and 2 sevens, which if you play poker, that would be a full house instead. So basically, we want to get just 3 of a kind and junk for the other 2 cards. So we want 3 of a kind, and we don't want like another pair or something like that, okay? So that's the setup. So notice that we're asked for the probability here, not the number of ways this can occur. So we need to make sure and answer this correctly as a probability question. So I think it's going to be easiest if we fill out the bottom first. So let's do that. That's the total number of ways our experiment can occur. There are 52 cards, and we're going to draw 5 of them. So it's C, 52 card, 52, 5. This is going to be combinations, not permutations, because the order that you draw the cards doesn't make a difference. There's nothing stopping you from shuffling the cards in your hand or anything like that. You just either have the 3 of a kind or you don't. So the order the cards are in doesn't make any difference. Okay, so now we want to know the probability of getting exactly 3 of a kind. So this is going to be kind of interesting, a little bit of a complicated question. So we need to break it down using the fundamental counting principle. So when we say 3 of a kind, we probably should decide what that kind is going to be. Is it going to be 3 tens? Will it be 3 queens, 3 jacks, 3 aces, 3 fives? What will it be 3 of? And so we have to decide on the rank of that triplet. And so there are 13 choices there, okay? So let me make a note to us. This is 13 of what? That's just, sorry, 3 of what, not 13. There are 13 choices for what our 3 of a kind are. Is it going to be 3 sevens? What is it? Okay, so there are 13 choices of what that's going to be. Okay, let's say I'm just going to build up the hand. So let's say that we decided it was going to be 3 sevens. Okay, and so the next thing we have to decide is, well, if it's going to be a triplet in sevens, it could be the hearts, clubs, and diamonds, or the hearts, spades, and clubs. Which 3 out of 4 of those sevens could it be? We've determined that we're not going to count the 4 of a kind case here, so that means that we can have only 3 sevens. Which 3 will we have? So that sounds like combinations. Out of the 4 sevens, or whatever that triplet is, out of the 4 cards, we're going to pick 3 of those cards. Okay. All right. So now we have 2 more cards to pick. All right. So we've decided, let's say that our 3 of a kind is going to be in 7s. So when we go to choose that 4th card, if we've determined that the other 2 cards have to be different from one another, then that means that from the original deck of 52 cards, we will be subtracting those 4 7s because 3 are already chosen and 1 we're not going to allow because we're trying to exclude the 4 of a kind case. So that means that there are 48 cards left. Okay, so there's 48 choices for what that 4th card could be. Okay, let's say that that card comes up a jack, okay, whatever that is. So if that card is a jack, we don't want the 5th card to be a jack because then we'd have a pair for our last 2 cards. So whatever that 5th card is, it can't have the same rank as our 4th card. So we're going to subtract those 4 jacks or whatever they are that came out 4th. That means that there are only 44 cards left to choose from for the 5th card. Okay, so this is how this plays out. So let me just recap how this calculation goes, and then I'll get us an answer for it. So the denominator was no restrictions. Out of 52 cards, 5 are picked out. How many ways can that happen? That's down here in the denominator. Okay, out of 52, 5 are picked. Okay, we're trying to build a hand that is 3 of a kind. We have to decide what is it going to be 3 of. 3 7s, 3 10s, 3 jacks, what is it? There's 13 choices for what that could be. Ace, 2 through 10, jack, queen, and king. Those 13 choices we have are represented right here by this 13 in the numerator. I decided just so we'd have a concrete example to look at that it was going to be 3 7s. Okay, if it's going to be 7s, I'm choosing, or whatever it is, we went 3 of them. That means that we have to decide out of those 4 possible cards, 4 7s, hearts, spades, diamonds, clubs, which 3 will make up that triplet. That's where this C4-3 comes in. Out of the 4 7s, which 3 will be chosen? Okay, so starting with a fresh deck of cards, we've decided what that triplet's going to be. It's going to be 7s. So that means that we're not having any more 7s in the rest of our hand. So there's only 48 cards left. So that's where this 48 comes in this numerator. After we've discarded or used the 7s, there's 48 cards left. Then you pick that 4th card. Let's say it's a 3. Okay, if this 4th card ends up being a 3, then the 5th card can't be a 3 because we're not going to allow pairs here. So that means that from those 48 cards, we're going to exclude all 4 of the 3s. 1 is going to end up in the hand, the other 3 will be just discarded. So there are 44 possibilities or 44 choices for what that 5th card would need to be. All right, so that is a little complicated, but hopefully you're starting to get the hang of that. Let me get us a decimal answer for this. All right, so that ends up being right around a 4% chance after all that. Okay, so let me know if you have any questions on that example. All right, so for our next example, this will have to do with the Super Lotto. So the way that the Super Lotto is played is you pick 5 numbers from 1 through 47, and then additionally what's called mega number from 1 to 27. Either by quick pick or picking your birthday or whatever you've done. So 5 numbers from 1 through 47 are chosen, and then a number 1 through 27 is chosen. So what we want to do, what the question is, we want to find out what the number of tickets are, possible tickets are, and then what the probability of winning would be. So the number of possible tickets. So there are 47 numbers to choose from, and we're going to choose 5 of them. Here it's going to be combinations because the order you fill out the little play slip in doesn't make any difference, right? The numbers are either selected or they're not. And then for our last number, there's just 27 choices. So you can write this as 27. If you really want to write C27-1, you can. But note that there's really just 27 choices for that. Okay, so let's see what we get. So there's 153939. 27. Okay, so that's 41416,353. So there's about 41, just under 41.5 million possible tickets. So then the probability of winning, of course, they have different prizes if you win, get like some subsets of the numbers, but let's ignore that and just say the probability of getting the 5 regular numbers plus the mega number. So the probability of winning then is 1 in 41,416,393. Well, that's a 5 rather, sorry, 353. Okay, and then as a decimal, okay, a really tiny number. Okay, it's like 2.41 times 10 to the minus 8. Okay, so a really small number. All right, so that really tiny number is really hard to visualize. 1 in 41,416,353, and especially if you rewrite that as 2.41 times 10 to the minus 8 power. So that's hard to visualize. So what I did next, and just for fun, was to see if we could put that down kind of in terms of a length. So here's what we've got. Suppose we wanted to think about the distance from COD to Disneyland. Hopefully you've gone to Disneyland. You know roughly how long that is. It's about a 2-hour drive depending on traffic. It's about 106.3 miles according to Google and according to this particular path using the 10 and the 91. So it's about 106.3 miles. So what I did was I took that probability of winning, the 1 in 41 million number, and multiplied that by the length or the distance from COD to Disneyland in miles, and then I'd converted that to inches. And it ends up being about 0.162 inches. So a way to interpret that would be this. When you go to buy the lottery ticket, the Super Lotto Plus, your chance of winning by hitting that one particular ticket, that one ticket in proportion to the total number or total possible tickets is like the distance between a COD and Disneyland, and a length about the width of your pinky fingernail. Okay, so let's say that you were going to bet $1 that you could stop your car, let's say, right on this little length, half the width of your pinky nail, somewhere between COD and Disneyland, and we're not going to tell you where it is. I'm going to choose a place at random that's going to be this wide, somewhere on the freeway between COD and Disneyland, and you're going to have to guess where that is. Okay, and so your chance of winning that Super Lotto Plus is the same as your chance of guessing that half a finger width distance. Somewhere between here and Disneyland. All right, so thinking of a small number sometimes can be helpful if you think or in terms of a length. So that was the point of that example. Okay, moving on. All right, so this one I've already worked out for us because we've seen this problem actually like twice already. At least in 2 different ways. So 4 cards are drawn from a deck of cards without replacement. We want to know the probability at least one will be a face card. We originally saw this problem in the context of the complements rule, and then also I'd showed you a really long way of working it out by doing it directly by counting it up each case separately. To try it a different way, we can use combinations. So this still divides it into cases, but the calculations are a little bit easier. So the possibilities are 1, 2, 3, or 4 face cards. In each case, the denominators are out of 52 cards, 4 are chosen. What varies is the numerators. When there's one face card, there's 12 total face cards in a deck of cards, right? So out of the 12 face cards, 1 is chosen. And then out of the 40 non-face cards, right? There's 52 total cards. If 12 are face cards, 40 are not. So here this is saying we're going to pick 1 face card and 3 that are not. In the second row, there are 2 face cards and 2 that are not. In the third row, 3 face cards and 1 that is not. And then in the last row, 4 face cards and 0 that are not. And then, of course, the possibilities done using the formulas, and then we just add the probabilities. And once again, we get 0.6624 as we did when we calculated this before. I just wanted to show you how you could work this out yet another way. So we've done this directly, which was super long. We did the complements rule, which was a lot better. And then now we've done this one. All right, so our last example for this section has to do with the birthday problem. And so let's take a look at this. The birthday problem is kind of a semi-famous problem in probability, but hopefully you'll find it interesting. So the story goes like this. In a group of n people, such as yourselves, or people in your household or anywhere else, in a group of n people, what is the probability that at least 2 would share a birthday? So what if we had 2 people in this class? You know, what is the chance that you have the same birthday as yet another person in this class? Okay. What is the probability that at least 2 people share a birthday, or maybe more, which is going to be less likely, but at least 2, some birthday in common? There's a couple of assumptions we're going to make when we calculate this. One is that there's no leap years. Leap years are going to make things really complicated, so we're going to just ignore that. And then secondly, we're going to assume that birthdays are equally likely, right? Which probably is not true. Maybe more people are born in November, right? But we're going to assume for the purposes of this example that birthdays are all equally likely and there's no birth. Nobody's born, there's no leap years. Okay, so we're going to try to develop the solution to this by thinking in a little problem, and then we're going to extend it into kind of the general case. So first of all, we want to figure out the probability that 2 people have different birthdays. So if 2 people have different birthdays, then that's the complement of them having the same birthday, right? In other words, if they have different birthdays, then it's not true that they're the same. It turns out that using the complements rule is going to be easier on this, okay? So the chance that they have the same birthday, well, the first person, there's 365 possible days in the year, and then the possible choices, let's say they could choose what their birthday is. The number of possible choices for what their birthday is 365, okay? So that's 1, right? It really doesn't help to have that in there, but it's going to help show the pattern. Okay, so there's in the denominator 365 days in the year. In the numerator, there's 365 possibilities for what that first person's birthday is going to be. Okay, if we're trying to figure out the probability that this person's birthday is different, there's still 365 days in the year. But if we want the second person's birthday to be different, it's going to be, there's only 364, right? Because that first day is chosen by that first person. So then that right there is the probability their birthday is different. This here then, taking 1 minus that, would be the probability that their birthdays are the same. So this is the different birthdays part. And then here the same. Let me put that down here. Same. That will be the 1 minus piece. Okay, so let's go ahead and calculate. It's about 0.997. And then complement 0.003 about. Okay, so about 1/3% chance that two people would have the same birthday. Okay, so let's try extending that same thinking to three people. So first, different birthdays. There's 365 days in a year, and the first person, let's say they choose their birthday, they got 365 choices. Then for the second person, there are still 365 days in a year, but now there's only 364 choices for that person. Okay, and then by the time the third person goes, there's still 365 days in the year, and then there are only 363 choices left. Okay, and so then if we want to calculate the same, what the probability is that it's the same, that's going to be 1 minus this answer. So let me calculate that for us. All right, so how it's looking for three different people is about 0.9917 that they have different birthdays, and then about 0.0082 that there's two birthdays in common among three people. That's still under a 1% chance. You can tell by now that this is going to take us a long time to get to something interesting if we proceed in this way. So let's see if we can start picking up on the pattern yet. So in each case, we're going to end up doing 1 minus because we need to use the complements rule to get the sharing the birthday rather than distinct birthdays. In the denominator, it's 365 basically multiplied by itself n times, where n is the number of people there are. And then in the numerator, we have 365, 364, 363, and we're counting down by 1. We're not counting all the way down to 1 to where we could use a factorial, though. We're just counting part way down. So it turns out that the permutations formula can help us with that. So to illustrate that, let's put the birthday problem on hold for just a second and say, let's go back to like our horse racing problem that we had before and say, well, we have 8 racers and we're going to pick the top 3, and they're going to win a prize, like a first and second and third prize. So it matters what order the horses come in, right? So it's permutations, and we saw that that was going to be P8, 3. And so if you go through the formula, that's 8 over 8 minus 3 factorial, 8 factorial over 5 factorial. And that's 8 times 7 times 6 times 5 factorial. And then we saw that that 5 factorial in the denominator canceled, leaving us 8 times 7 times 6. And if you thought about it, it probably occurred to you before, well, couldn't we just do it like this, right? If there's 8 horses, there's 8 choices for whoever the winning horse is. That horse finished the race, so there's 7 choices for the second horse. Once those 2 horses have finished, there's only 6 horses left for the third place finish. So that's 8 times 7 times 6, and that's consistent with what we got using permutations. So you'll notice that here, taking 8 permutations of 8 things, 3 at a time, gave us this calculation, 8 times 7 times 6, which starts at 8 and counts down by 1 and goes a distance of 3 numbers. So we can use that permutations here in this context with the birthday problem. So let's try it. So we'll say 1 minus, and then I'll have a numerator with permutations in it. Down below, we have 365 cubed, right? 365 times itself 3 times. Here, there was in the numerator 365 total days, and we needed to choose basically the first 3 of those numbers. So we'll say 1 minus P, 365, 3. So it turns out that that will do it for us. And what's nice about this is it gives us a general formula, and we won't have to go through all these calculations for a whole bunch of different group sizes. Okay, so in general, our solution looks like 1 minus P 365N and that's divided by 365 to the n power. So your calculator may have a little trouble with that size of permutation or that size of raising, 365 to a huge power. You could use a computer. I'm going to show you here in a second how you can do this on Excel, and we can see kind of some nice results. So that's coming up right now. All right, so I've put the formula into Excel so that we can calculate some of these probabilities more easily and also see a nice graph. So that's what you're seeing here. There's group sizes ranging from 0 up to 50 as shown. One thing worth mentioning is that for 0, it's showing a probability of 0. The probability is not actually equal to 0. It's just that if you round it to 3 decimal places, it appears to be 0. It's just really small. And then, of course, we have this graph as shown. The horizontal axis is the group size, and the vertical axis, of course, the probability. You can see that the probability is increasing towards 1 as our group size increases. And then I didn't use a very big x-axis, but that's okay. Gets pretty close to 1 pretty quickly. You can see that if you get a group size of about 40 or so, like your size of your typical class, 35, 40, there's like an 80 to 90% chance that at least 2 people will share a birthday. So that's pretty interesting and kind of a nice application of some of the things that we've learned recently in this section. Also down below, you can see the Excel formula for permutations. There's a function in Excel for permutations, PERMUT. The first argument is the n, the second argument is the r for that. All right, so that finally takes us to the end of this section. Let me know if you have any questions on it, and have a great day.